Okay, so let me talk about the midterm exam. Midterm exam is next week. It's an hour and a half long, 35 questions, all multiple choice. I know, multiple choice, it feels kind of awful, but it will be okay. I will provide Scantron forms for you. You will need to bring your reference tables, so please make sure you bring your reference tables. Bring your calculator, pencil, eraser, all that stuff. An ID. I have to check IDs. I know it seems silly, but someone in the past tried to sit in for someone else, so now I have to check IDs. Okay. Let's see, it'll cover everything that we've covered up through today. I don't know, other questions? Yes?
Will the questions resemble ones on the quiz? I mean, quizzes, will they be similar in type, or will they be like more conceptual, or?
Yeah, that's a hard question to answer. So I write the quizzes, and I wrote the midterm exam. So they're all coming from my brain, right? So in terms of that, like, I feel like they are somewhat similar, but I mean, there might be a few conceptual questions in there. The final exam will definitely have some more conceptual questions. Only a couple. There's one question on R, which is similar to the R questions that I put on the quiz. It would be like, how would you answer this question using an R command? And it would be either a binomial or a normal distribution question. So those things you should be familiar with. Yes, question.
You get one sheet for notes.
You get one sheet of notes, yeah.
Board or
Just the front. For the final exam, you can write on both sides. Okay, so please make sure you only write on one side. I'm going to do a note sheet check. I don't want to confiscate anyone's notes if there's writing on both sides. Yes?
A sheet of paper or 3 by 5?
A sheet. So letter size paper, 8.5 by 11. So don't bring in like tabloid size or legal or something. Just standard. Yes.
If we come early, we got our quizzes next week.
Yes. Yeah, I'll have them graded and I'll return them to you guys.
Is it the midterm covers chapters 1 through 6?
Yes, it'll cover chapters 1 through 6, up through everything we've done today. So things that were not covered on the quiz that will be on the midterm will be like the confidence intervals that we covered last week, and we'll do more confidence intervals today. Okay.
standard error and stuff like that.
Yeah, standard error. I mean, yeah, that's part of confidence intervals. Yes?
The R commands, like what would we be responsible to know?
Just, I would say you should know how to do P norm, Q norm, D binom, and P binom. If you know those four, then you should be okay. And it's just one question out of 35. Yes?
So which includes today's lecture?
What is today's lecture?
It includes, the midterm includes today's lecture?
Yes. Today's lecture, I am doing confidence intervals based on for the difference between two means from two samples. Okay? And so in terms of new material, it's short, and then the rest of the class will review things. And then I will also, so I'm also assigning a lab that's not due next week, but it's due the week after. So for next week, I would say study for the midterm. Do this week's homework and study for the midterm. And then the following week, you'll have a lab due. And so I'm going to show how to work through that lab today, and but then next week after the midterm we do have lecture, but it's going to be covering. We're going to enter chapter 7, so that's just how it goes. So, yes.
You mentioned on the website that you were going to give us some extra problems, I guess. Or is it we just rely on homework?
Some extra problems. Okay, did I say that? All right. Well, we'll do some review today, and then maybe I'll point you in the direction of additional problems to solve there. Okay. All right. With that, we'll start. Okay, so we'll continue. Chapter 6. Okay. So last week we created a confidence interval. For mu based on a sample. Okay. And we said basically we assume that it's a random sample. And then an n should be large enough, but also not too large. We said if your sample has these properties, size n, mean y bar, and standard deviation s, then the confidence interval is going to be y bar plus or minus t star times s over the square root of n. Okay, where t star has degrees of freedom equal to n minus 1 of the appropriate confidence level. I kind of want to break down our confidence interval, y bar plus or minus t star times s over the square root of n. T star is known as our critical value. S over the square root of n is our standard error. And y bar is our point estimate of the parameter. Okay. What I mean by point estimate of the parameter is that what we are trying to do is we're trying to estimate mu. Okay? Mu is the mean of the population, so that is a parameter of the population. It's something that is defined by the population. And when we take a sample to try to estimate mu, our best guess is y bar. Okay? And because it's just a single value, we call that a point estimate. If we were to take another sample, we would get another y bar, and that would be a different point estimate. So in order to talk about a confidence interval, we have we give ourselves some breathing room, and that's found by doing the critical value times the standard error, and those two together are known as the margin of error. Okay, so and again, the whole point of a confidence interval is that we don't know the properties of the population, and so based on what we observe in a sample, a single sample, we're trying to draw conclusions about the population. Drawing conclusions from limited data. Okay, so today we will make a confidence interval for mu1 minus mu2. Essentially, we have population 1, or we have a sample, okay? We have sample 1, which comes from population 1, okay? And then we have sample 2, which would come from population 2. And the question we want to know is, well, based on what we see in sample 1 and sample 2, does that mean that what does that tell us about the difference in means of population 1 and population 2? Okay. What we see in samples 1 and 2 that tell us about the respective populations? Usually, the question we're interested in is, do the respective populations have different means? So, for example, let's say we took we'll call this sample 1. Let's say we selected 12 random men. Okay, and we measured their IQ. So let's say the average IQ, so we'll say y bar will be 102, and the standard deviation we will say is 15. And sample 2, let's say we take a sample of women, let's say 15 women, also randomly selected. Okay. And for sample 2, y bar, let's say, is 100. And the standard deviation is 16. Okay. So the average IQ of the 12 men and the average IQ of the 15 women are different, okay? So these 12 randomly selected men had an average IQ of 102. Over here, the average IQ is 100. What does that tell us about the respective populations? Does this provide evidence that the average IQ of men is higher than that of women. Okay, well, we just have a sample of 12 men and a sample of 15 women. What does that say? Okay, is that enough? Is that not enough? What does this mean? Okay, that's what we want to know. What do these samples tell us about the respective populations? Okay. So for this, we're going to create a confidence interval for mu1 minus mu2. So what we see, okay, we observe. So I'm going to say, to distinguish between the n and the y bar and the s of sample 1 and that of sample 2, I'm going to put subscripts, y bar 1 and s1. And we write this as n2, y bar 2, and s2. Okay, so we can keep track of them. So what we observe is that y bar 1 minus y bar 2 is equal to 2. All right? Our two samples that we randomly selected have a difference of 2 IQ points. What does that say about the respective populations? Okay. So we want to know, what does this say about mu1 minus mu2? Okay. So mu1 minus mu2, that would be our parameter that we are interested in. We are interested in the difference between the parameters. Okay. Well, there's a few approaches that we could use, all right? And one, a simple approach, but this turns out to be the naive approach, would be to just create a confidence interval for mu1 based on the sample of men, and a confidence interval of mu2 based on the sample of women, and just see, how do our confidence intervals look, okay? We run into some problems there because let's say, I don't feel like drawing this, but essentially, if you do that approach, create individual confidence intervals, and just to see if there's any overlap, it turns out that you're overestimating the standard error. Okay, the standard error in that case would be you're just adding the two standard errors, and that would be it ends up being too large. Okay, and so when we're dealing with a difference between two populations, if we're assuming that they are independent, okay, the two sample means to combine them. Okay, so the standard error. Sorry, not the sample means. The standard error of mu1 minus mu2, not mu1, y bar 1 minus y bar 2. The standard error of this sampling distribution is not S1 over the square root of N1 plus S2 over the square root of N2, okay? We might feel like just adding the two together, but this turns out to be too big, okay? What we want to do is we want to add the variances and not the standard errors themselves, okay? So it's actually, what we want to do is we want to take this and we square it, plus S2 and then we take the square root of that, okay? And so what we end up getting, the standard error of y bar 1 minus y bar 2 ends up being the square root of s1 squared over n1 plus s2 squared over n2. So this is what we have. So you kind of get this slightly ugly formula, and there's nothing we can really do about it. This is just the standard error. When you combine, when you're taking the difference between two sample means. Yes?
It's the absolute difference, right? Between the other, or it doesn't matter at all. Why is it 1 or 2 and it's 100 the other way? I don't know if this question is even.
Yeah, the sign does matter, but I'll talk about that later, okay? I'll talk about that later. Okay, so with this is our standard error, and that's just what we have. When we make our confidence interval will follow the same form as the confidence interval for one sample, except we have a different point estimate and a different standard error, okay? So our confidence interval for mu1 minus mu2 based on y bar 1 and y bar 2 is y bar 1 minus y bar 2 plus or minus t star times the square root of s1 squared over n1 plus s2 squared over n2. Again, this will serve as our point estimate. Of mu1 minus mu2. This is still our critical value. And this is our standard error. Yeah.
These two samples must come from different populations, or can they come from the same populations?
Well, that's essentially what we're asking. We're asking, when it comes to IQ scores, can we consider men and women to be the same in the same population? That's what we're essentially asking here. Okay. So on a surface, we just, here's a sample of men, so that comes from the population of all men, and then here's a sample of women, so that comes from the population of all women. So just based on these two samples, can we say that this is that they could be treated as the same population? Okay. And our answer will probably vary very heavily on like which country, from which country we're taking our samples. I think places where access to education is not the same, we will see a difference because that plays a part. All right, so let's just make a confidence interval here. So we do y bar 1 minus y bar 2. We do 102 minus 100. So we get 2 there, plus or minus our t star times s1, 15 squared over n1, 12, plus 16 squared over 15. All right, and so now we have to choose our t star. Okay, and so for this we're going to go to our t distribution. But selecting t star, our critical value, requires that we have a degrees of freedom. Okay, and so there is a way to calculate the degrees of freedom, but to get the true degrees of freedom is a complicated formula that I feel is not necessary to learn. Okay, so the true degrees of freedom, it's in your book on page, where is it? On page 206, about a third of the way down the page. Okay, the true degrees of freedom has a complicated formula. Okay, and so there's two approximation methods. Okay, there's maybe like playing it safe, and then one is you know, playing it a little, I don't know, not dangerously, but so two methods to approximate this complicated formula. Okay. If you create a confidence interval with a computer, it'll get you the actual degrees of freedom based on this formula very quickly. Okay, but to do it by hand, it's kind of a pain in the butt, so we're not going to bother. Okay, so to get the approximate degrees of freedom, method 1 is to do n minus 1 and use the smaller of n1 and n2. Okay, so in this case, we have 12 men, 15 women. We would use the sample of 12 men, and our degrees of freedom would be 12 minus 1, 11. Okay. The other method, which is the one we're going to use in this class, is to do n1 plus n2 minus 2. Okay. So we would do 12 plus 15 minus 2, and we would use 25 degrees of freedom. Okay. And the true degrees of freedom will always be between these two numbers. Okay, so you can have an upper bound and a lower bound. This is the one we're going to use. Okay.
Is it always minus 2, or is it just because of?
It's always going to be minus 2 for this approximation method. Okay. All right. So for this one, you use n minus 1 using the smaller n. And this one, it's n1 plus n2 minus 2.
Which one's the more dangerous one?
This is the quote more dangerous one, all right? In that this will always give you more degrees of freedom, which basically puts a little bit more stake in your. Basically, it creates a slightly narrower interval than what it might truly be. Okay, so I think last week I talked about the trade-off between having a narrow interval versus confidence. Okay, when you use this, it's always going to give you just a slightly more narrow interval than what it might truly be. Okay, and so I don't know. That I guess just take that into account. So you think you're 95% confident about the interval you have, whereas it was actually a little bit more narrow, so maybe you should have been less confident about it. Okay. So you should have only been 93% confident or something, I don't know. Okay, so anyway, we'll try this out. So for our degrees of freedom will be 12 plus 15 minus 2. Then we'll have 25 degrees of freedom. Let's say we make a 95% confidence interval. Our T star will be equal to 2.060. So, did I read the table correctly? Okay. So, plugging in 2.060 right here. Punching this into my calculator. Plus or minus that. 5.9847. So I have 2 plus or minus 12.33. Okay, and so my confidence interval goes from negative 10.33 to 14.33. What does that confidence interval mean? Alright, so this is our interpretation. So it goes from negative 10.33 to 14.33. I would write, I'm 95% confident that the mean IQ of men is between 10.33 points, 10.33 I guess points lower, and 14.33 points higher than the mean IQ of women. So it sounds funny to write that. Okay. Sounds funny to write something like that, but it should, okay? Because essentially, you're basically asking, is thing A bigger or smaller than thing B? Okay? And your answer is, well, I'm pretty confident that thing A is either bigger or smaller than thing B. So what does that mean? That means you don't know if one is larger or smaller. Okay? We're saying, is the mean IQ of men higher or lower than the mean IQ of women? And basically we're just saying, I'm confident that it's either lower or higher, or somewhere in between. Okay? We're basically saying that the mean IQ is not going to be 100 points lower than the mean IQ of women, and the mean IQ of men is not going to be 100 points higher than the mean IQ of women. But do we know if it's lower or higher? We don't know. Okay? So based on this, basically, is 0 a possible difference for the mean difference between the mean IQ of men and women? Yeah. Yes. Okay. 0 is in between negative 10 and positive 14. So 0 is between the ends of the interval. Or we might just say 0 is within the interval. Okay. And so because 0 is within the interval, so we do not have evidence to say that there is a difference between the mean IQ of men and women. that satisfactory? Okay, so let's try this. So based on our sample of 12 men and 15 women, even though the sample produced an average IQ of 102 over here and 100 over here, and we see a difference of 2 points, that is not enough to to provide evidence that there is a difference between the mean IQ of men and women. But let's, rather than measuring IQs, let's take something else. Let's measure the heights of 12 men and 15 women. Okay, so sample sizes don't really matter, but I'll just leave them as the same. Okay, so let's say the average heights of the men was 69.5 inches with a standard deviation of 3.1. And over here we will take, we'll say the average height was 64.5 with a standard deviation of 3. Okay. So 12 men, 15 women, this is what we observe. Is this enough to indicate that there is a difference between the average height of men and the average height of women? Okay. So from our day-to-day experience, because we have seen more than 12 men and more than 15 women, we know that the answer is that there is a difference between the average height of men and the average height of women, and the average height of men is taller than the average height of women. Okay, we know that that's the answer. The question is, based on these two samples, is that enough evidence to also indicate that? Okay. Whereas the debate about IQs is largely unsettled. Nobody knows the answer to that, if there truly is a difference between the average IQ of men and women, at least in the US. Okay, so let's see what we have right here. All right. Well, actually, why don't you guys make the confidence interval yourself, and then we'll check our answers. Sorry. Huh?
What was it?
That I touched the connection, so it creates static.
Is this the 95%?
Yeah, we'll stick with the 95% confidence interval. Okay, let's try to answer this. So I put that. So what we observe is we observe a difference of 5 inches between the mean height of the men in our sample and the mean height of women in our sample. Okay. I didn't change the sample size, so N1 plus N2 minus 2 is still 25, and for 95% confidence interval, our T star is still going to be 2.060. And S1 is going to be 3.1 squared over 12 plus 3 squared over 15. And if I did my calculations correctly, I just erased it. I'm getting 1.1836. Multiply that by 2.060, and I get 2.44. Is that?
Oh no, I had a dramatic
I'll add it here. Alright. And 5 minus that will be 2.56. Okay. Okay, so our 95% confidence interval goes from 2.56 to 7.44 inches. Okay. I hope my math is correct. You guys, it verifies? All right, good. So then we would say I am 95% confident that the mean height of men is between 2.56 and 7.44 inches taller than the mean height of women. Okay. So I'm confident that the average height of men is between about 2.5 and 7.5 inches taller than the average height of women. Okay, somewhere in there. Yes.
If you just said is 2.56 to 7.44 inches, you know, does it have to say specifically between, or is that doesn't matter?
Is
Or I mean, are you going to be a stickler for semantics?
oh, probably not. But you should say somewhere in there that this is the confidence interval for the difference between the mean height of men and the mean height of women. Okay? Because we're not saying that the mean height of men is 2.5 to 7.25 or 7.44 inches. Okay? Okay. The average man is not 3 inches taller, right? We don't have little little people running around. It's we're saying that the average height or the mean height of men is between 2.5 to 7.5 inches taller than the average height of women. Okay, so here we have indication that the average height of men is indeed higher than the average height of women. Okay, because 0 is not in between 2.5 and 7.5 inches, or 2.56 and 7.44. Okay, so 0 is not within the interval. Okay, so that means we do have evidence that there is a difference between the mean heights